For our project, we did the effects of distance on points scored in darts. The project was worked on by Peter McChesney, Annalise von Sprecken, and Dylan Burnett. The class was Statistics 212K. Introduction. So, darts is played by two people, and the objective is to throw the darts at a circular board and to outscore your opponent. In the professional world, it is played by standing at a distance of 7 feet and 9.25 inches away from the board. The board is divided from different levels, with each area containing different point values. For the description of our experiment, the goal was to find whether adjusting the OSH, which was the distance from the dartboard from where the thrower stands, would have a significant difference on mean score of the dart throw. So, in our experiment, we measured with tape on the floor distances of 6 feet, 8 feet, and 10 feet from the dartboard. To determine the order in which we throw at each distances, we used a random number generator to decide which distances to throw at each time. We threw a total of 25 darts, which equaled to a total of 75 throws. We recorded point values that each dart landed on.
So this portion of the slide shows the means procedure that we did using SAS. It gave us the different sample means and standard deviations for the three distances. That would be a sample mean for 6 of 10.6, for a distance of 8, 11.48, and a distance of 10 being 10.44. Next, we used the correlation procedure. Sorry, that's my dog. We used the correlation procedure for getting the correlation coefficient and the p-value. We found that it was a very small negative correlation coefficient and then a large p-value. That will be explained more in one moment. Next slide. So we move on to the side-by-side box plots. Here it basically just shows you that for 6 feet there's a slight right skew, for 8 feet there is no skew, and then 10 feet there is a slight right skew. It also shows just the measure of center spread and all that information here by showing the different quartiles in the extremes by distance box above. And then in the overall statistics box, it shows you the overall mean and then pool standard deviation. Moving on, you go to the dot plot. Basically, this validates what we were looking at earlier with the fact that there is no linear correlation between 6, 8, and 10 feet. When you have a p-value as high as it is for us and then a very small negative correlation value, then it just validates there's no linear correlation. So, yeah. Next, we move on to our ANOVA findings. So we used the GLM procedure for this, and first we looked at both the p-value and f-value. So basically it shows that there's no evidence to reject the null hypothesis, that being that all of the distances are equal. That means that at least one of them are different. We found the p-value to be 0.8672, and then the f-value to be 0.14. That means that the variability attributed to the different distances is 0.14 times greater than the variability attributed to random chance. Next, we have the simultaneous confidence interval findings. So we used Bonferroni's adjustment here to compensate for any potential type 1 errors. There are 3 confidence intervals to account for. So each individual hypothesis is calculated at a significance level of 98.3, this being because 0.983 to the third is 0.95, with an alpha level of 0.05. That means that we are looking for 95% confidence. All 3 intervals captured the value of 0, so there's no evidence that there's a difference between any of them. Next is findings for regression. First, we provided a scatter plot that has the regression line superimposed on it. Then we have a table that includes the parameter estimates, p-values, and r-squared for the regression model. Our r-squared value in this situation was 0.001, indicating that 0.1% of the variation in the points scored can be explained by the distance standing from the board. An example scenario where the line in our regression model can be used to make an appropriate interpolation for our data is if we plug 9 into our regression model, then we could interpolate the confidence interval for the approximate point value. So when we did this, we received a predicted value of 10.8 and then a confidence interval ranging from negative 4.0311 to 25.6311. Then lastly, we went to our assumption checks. This was for the regression and ANOVA. For the regression, we were dealing with the QQ plot, checking to see if it follows a 45-degree line for both 6, 8, and 10 feet. As you can see to the left, the QQ plots, that all of them follow very closely to a 45-degree line, so they appear to be normal for the residuals. Then for the ANOVA assumption checks, everything here seems approximately normal despite the small skew that we saw in the box plot. It looks that they all have equal variances in the 3 groups, and that none were really double or more than another. Everything was done with a random sample through a random number generator, so everything here seems to follow.
So just to summarize everything we found in this experiment, originally we thought that the 6-foot throwing distance would have the highest population mean because it was closer to the board, so there was a higher rate of accuracy there. But after running the numerical summary and looking at the dot plots and box plots, we found that they all had very similar population means, and looking at the distribution of each of the plots, we saw that they overlapped a lot, which led us to believe that there was probably not going to be a significant difference between the population means for the 3 throwing distances. After running ANOVA, we found a high p-value of 0.8672, which meant that there was just no evidence to reject the null hypothesis that the population mean points scored were all equal, so it just further supported our idea that there wasn't going to be a big difference between them. When we ran the simultaneous confidence intervals, we found that there was no significant difference between the 2 true population means of the points scored from each throwing distance. Each of the confidence intervals captured 0, which just showed that it could have been positive, it could have been negative, so there was no evidence there. And then the regression line had a very high p-value associated with the slope, which just further emphasized the idea that there wasn't a relationship between our x and y variables, or the distance stood from the dartboard, and the points scored. And it had an extremely small r-squared, or correlation coefficient, which just further emphasized that there wasn't a big correlation between our 2 variables we were looking at. So all of our findings supported the same idea that there was not a strong relationship between the distance stood from the dartboard and the point scored, in that all of the true population means were probably very similar for each of our 3 throwing distances. And due to the distribution of our data, we feel like the regression line was the better estimate because the distance stood from the board and the point scored didn't have a relationship. It didn't really matter, so you could estimate that wherever the thrower stood, in this case Dylan, he would have a fair likelihood of always scoring the same amount of points. For limitations and what we could have done differently, we thought maybe next time if there was a larger distance between each place the thrower stood, we might see a bigger difference between the points scored. And because we only used 1 thrower, we can only generalize our findings to Dylan's throwing and not to the general population. So next time we could have multiple participants and seeing how it affected everybody's throws, just to see if there was a larger trend you could trace among multiple people. And this is the source we used to find the rules for professional darts.